Hello, today I'd like to talk about selecting a motor in machine design. I'd like to use an example that we did a number of years ago where we wanted to design a lightweight gripper to put on the end of a reacher for a person to use who had a disability. So it needed to be lightweight and didn't need to really grip with a lot of force. Needed to be able to grip with 4 pounds of force on the output fingers, and it needed to close those fingers about 4 inches and just a little over a second. So that was the output of this, and what I'd like to do is kind of think about starting with the output and working backwards so that we can select the particular motor that we want, and then we can establish the various gears that we have, gear ratios, gear reductions, the 4-inch arms that we had, the worm stage that we had, and then the planetary stage that we had, and then the brush motor. So I wanted to talk about the process that was used to establish those items. Basically, we start from the output. We want to know what needs to be delivered, and by that I mean you want to know the output speeds, the loads, and the power. So in my simulation of that system, you can see that it starts from a open position, and then it comes and grabs a simulated item. So there's two scenarios here in the design to consider. There's a scenario 1 where it is loaded, that would be at the end of the grab, and then there's a scenario 2 where you're really running unloaded before you even grab anything. So these are the scenarios that we're going to focus on. We want to move when it's unloaded a distance 4 inches between the two fingers, and we want to do that in that 1.25 seconds. Once it starts grabbing something, we want to, within 1/10 of a second, we want to be able to move about 80 thousandths of an inch. And based on those two things, we can establish what the speeds are. Here, my speed on the unloaded configuration is going to be that distance divided by the time, divided by the radius, and then divided by, of course, 2, the number of fingers. And then there's going to be some unit conversion that you see over here that gives me my RPM. And that RPM is actually going to be for what the worm gears need to do. So that's what that is about. And then as far as the output torque, I want to take that 4 inches that we have on the output finger, and I want to include that radius, that 4-inch radius for the arm. And of course we have the two fingers, so the output torque that's on each of those worm gears is going to be simply the force times the radius, and then since there's two fingers, we're going to have 2 that's going to be applied to the worm. So that's we're transitioning really from having a force to having a rotation. So we're almost where we want to be. And what I really did was I took that 32 inch-pounds for my TO, and I put it there for my loaded scenario, and I put the 1 RPM here. I put that in this location. So I've got my scenario 1 squared away, where I have my output torque. That is what's going to the worm gears, both of them, and I'm rotating those gears at 1 RPM. And what I did is I want to make sure I know what the power is, and the power is a simple function. You're going to take the torque in inch-pounds multiplied by the speed in RPMs, and then of course you have the necessary unit conversions. If you take a look at this one, for example, I've got B10, which is going to be B10 is going to be the output torque times C10, which is going to be the RPMs, dividing by 12 for that to get it into foot-pounds. Then I multiply by 2 pi to get it into radians, and I'm dividing by 60 to get it into RPMs. That's going to be foot-pounds per second, so I divide by 550 to get it into horsepower, multiply by 746 to get it into watts. So as you can see, there's not a lot of wattage here, 0.36. So we have firmly established, starting from the output, we have firmly established what we want, and that's what we do. We start from the output and we establish what we need to deliver. You start from out. You want to establish your output speeds, loads, and power. I've really done 2 speeds. I've done an unloaded and a loaded, and then of course for the power I have the loaded. So I've pretty much got this first thing squared away here, so I'm in good shape. The next thing you want to do is do a gross estimate of what your system efficiency might be, in order to so that you could estimate what the input power need to be. Let's see what I did there. So after the rotary output part, I looked at estimating what the machine efficiency might be, and that effectively I just took a shot at a third, because I know that I'm going to have a pretty large reduction, and kind of had already thought about a worm potentially with a planetary, so I kind of had an idea that it was going to be about a third, so I did that. And then my input power is basically going to be the output power that I originally had for my loaded scenario, divided by my estimated efficiency. So I'm going to be looking for a motor that can sort of provide this 1.1 level of wattage. Not a lot. So I kind of have this second step squared away, so I'm good for that. The next thing I'm going to do is I'm going to propose a motor that's based on that power. So I'm going to take a look at what my options are for that. And first thing I did was looked at Micromo, that makes some very nice high performance brush type motors. And the particular motor that I started looking at, neodymium iron boron, so very high performance. Really trust these. And I started looking at the 6-volt version of the 15. It's a 15 millimeter diameter motor. This is what it looks like, 15 millimeter diameter motor, and it's 24 millimeters long. Just to give you an idea. And what is its weight? Mass 18 grams, so it's not big. It says it's 5.3 watts. This is a German company, so the commas are used in place of decimals from the US perspective. So it's a 5.3 or 5 watt style of motor. And what I do is look at the rated parts as well. So I look at the rated torque and I look at the rated speed. So it looks like 2.9 millinewton meters, and it looks like 3860 revs per minute. So that is the level that we're going to be looking at here for our proposed motor. So the proposed motor is going to be a Micromo, and what I did is took the same equation that I used before, but basically adapted it for millinewtons, and it's simply the newton meters times the radians per second representation here. So the rated wattage of this proposed motor is 1.2 watts. So it is with a little bit of headroom above what we're kind of looking for. And the Next thing is that I put down the proposed motor's no load speed. So I've got sort of a motor rating in terms of rated wattage, and then I have a motor rating in terms of what its no load speed is. The actual no load speed is 9,500. Let's go take a look at that. So here under the 06 6-volt version, 9,500 is the no load speed that I wanted to take a look at. So we have effectively proposed an input motor based on the input power. So we have finished step 3 in the process. So next we're going to establish the kinematics. We're going to establish what happens between that proposed motor and what happens at the end where the finger is, how fast it rotates. We're going to do that based on our idea of what our optimal motor condition is going to be, and we already know what we want at the finger. So what we do is we establish some coarse idea of what our total reduction is going to be, and we're going to start with that we want that 3.8. Our worm gears, or our fingers, need to rotate at 3.8 RPM. So that's what we're targeting, and we know that the motor at no load would run at 9,500. Now I pared that down just a little bit. So if we're looking at getting something between a reduction between this motor of 8,000 RPM, sort of pared down a little bit, and that 3.8 RPM of what the fingers would be doing. So that's what this target total ratio is. It is C26 divided by C11. So that's going to be that 8,000 divided by the 3.8. So that's roughly 2094 for a total reduction. See, the motors want to run, I always say that, motors want to run at thousands of RPMs. Okay, so how can I do that? And what we do is we're looking at a worm planetary combination. So if I were to use a worm of 30 to 1 and a planetary of 69, you multiply those two together and the total reduction would be 2070. So this is what I'm proposing. I'm proposing kinematically a linkage between the motor running at 8,000 RPM and the output fingers running at about 3.8 RPM. So we've pretty much established what we want kinematically between the motor, the proposed motor, and those fingers. So next we're going to start looking at what the loads look like as we step backwards from the fingers back towards the motor. And we're also going to be estimating fine-tuning some individual efficiencies for the various stages. And then we're going to double check everything. So at the proposed worm stage, we're looking at a worm reduction of 30, and we're going to estimate its efficiency of the worm at a half. So what we're going to do is we're going to walk back the loaded 32 inch-pounds. We're going to walk that back, and we're also going to walk the two speeds, the two scenarios, the loaded and the unloaded scenarios. We're going to start walking those back, and the speed of the worm, this is the actual worm shaft. What we need at the worm shaft is going to be, speed-wise, is going to be the gear ratio, which is 30. It's a single start worm with 30 teeth on the worm gear. So we're going to be looking at the gear ratio times the output speed. So the loaded output speed was 1 RPM and the unloaded was 3.8. So that's going to give us 28.6 would be the 30 times the roughly 1. And then the 3.8 times 30 is going to be about 114. So that's our speeds based on just the definition of the gear ratio. It's going to be the speed of the worm. And then for the loaded one, what we're going to do there is we're going to look at the torque on the worm itself is going to be equal to the output torque for both of the worm gears. You're going to divide by the efficiency times the gear ratio. So the torque is going to be considerably less than the 32 that we needed. But you also have to account for the inefficiencies as well. This particular equation comes from the definition of efficiency, where you have the output work of that stage divided by the input work of that stage, and you can make a substitution for gear ratio. So, and then to get this equation, you swap the torque of the worm with the efficiency of the worm. That's where this comes from. I use this all the time. So that's how I got the 2.13 there. You can see this B10 is going to be that output torque divided by B34 is the efficiency, and C34 is the worm stage gear ratio. So that's how I got that. And then of course the wattage, just wanted to kind of keep track of the wattage, same kind of calculation as we had before. And then in anticipation of going to that motor, I started keeping track of torque in millinewton meters as well. So between this and this is simply a unit conversion, and it turns out there's about 113 millinewton meters per inch pound. So kept track of that, and then of course the power and the speeds are going to be the same. So that's got us one stage up, and then the next stage is where we're going to walk it back up the planetary. For the planetary, I've got a 69:1 planetary, and it's at 68% efficiency. So let's go take a look at that. For the planetary, I looked at the motor parameter sheet, data sheet here, and it says, hey, it can connect to a 15A planetary. So bring up the 15A planetary. The reason I like this and wanted to use the planetary here, the 15A, is because it's plastic. It's very light, and the three-stage reduction, they have a 69:1 there for me. This is what it looks like: 15 millimeter diameter connected to the end of the motor. And then it has a 3 millimeter output shaft. So that's what the planetary looks like. Keeps everything on center as well. And the other thing is very light, only 5 grams. So that's why I like that one. The efficiency, 68%. That's where I got that from. Okay, so basically what I can do is repeat what I did for the worm stage, and then figure out what the motor needs to spin at. So the motor is going to be the planetary reduction or gear ratio times how fast the worm is, or it's going to be the product of the two gear ratios times the output. Either way, the two scenarios, I've got a loaded scenario, which was equivalent to the 1 RPM of the fingers, and then I have an unloaded scenario, which was equivalent to the 3.8 RPMs of the fingers, like that. And then the torque of the motor is going to be a similar thing that we did before. We're going to take the torque of the worm and divide by the efficiency of the planetary and the gear ratio. That's the same thing as stacking it up like this, where you're dividing by the two efficiencies and the two gear ratios, and dividing that into that original 32 inch pound that we had before. So you can see our wattage is climbing up, and the torque of the motor, the torque is going down, speeds are going up, because it's a reduction. And again, what I did is I changed the torque of the motor from inch pounds into millinewton meters, again using that 113 millinewton meters. So static-wise, we're sort of okay here. There's one thing I want to point out that I'm not completely happy with. The planetary says that it's good for 250 millinewton meters, but this particular stage says intermittent torque, it's limited to 200 millinewtons. So that's a big gotcha there. So if I go back up here and look at what I need at the worm shaft, that is a little bit high. So I could actually put that in red here, bold it in red, so maybe a light red. Yeah. So yeah, so that's a little bit out of spec there. But for the most part, we have walked back all the way back to the motor, and we've got the 5.14 that we need at the motor shaft. It's only at 1 watt for that 1 RPM of the fingers. That's that first scenario. The second scenario is the unloaded speed. We said we could go up. We budgeted 8,000 RPM for that, so we're in pretty good shape there. This particular load here is less than the stall torque of the motor, so I feel like this is something that motor can do. So from a statics perspective and a kinematics perspective, we seem to be in pretty good shape here. So I would say, we're pretty much good there. The next thing I'd like to do is kind of look at some other things in the motor. What I'd like to do is to delve a little bit into how these motors work and what the bridging the gap, so to speak, between what's needed at the motor wires with respect to what's happening at the motor shaft. There's 3 really critical constants that you get from the motor. Of course, we've already talked about the stall torque, but there's 3 additional constants that you get with the motor. There's the torque constant, in this case is going to be millinewton meters per amp. There's the voltage constant, or the back EMF constant. That's going to be volts per 1,000 RPM. And then there's terminal resistance. It's a brush type motor, so there's really only 2 wires, and that resistance is between those 2 wires. If you measured it with a ohm meter, that's what you would get. You get these from the data sheet, so very, very important that you have a data sheet that you can trust. And like I said, from the Micromo, this is a really nice something you can trust type of thing. So we're looking at the 6-volt motor, terminal resistance 5.1, and the no load, we've already pulled that up, is 9,500. The stall torque, we've talked about that at 6.98. The back EMF constant, we want to bring that in as 0.628. Be very mindful of the units. So here it's showing millivolts per RPM. I've just changed it to volts per 1,000 RPMs. It's the same kind of thing, but 0.628. That's what I had here. Volts per 1,000 RPM is the same as millivolts per RPM. So we have that. And then the torque constant is 6 millinewton meters per amp. So those are the critically important values that you need. And what you're going to have is you're going to have the torque at the motor shaft is going to be equal to that torque constant times the motor current that's going into the terminal wires. Then you're also going to have the voltage of the motor, the voltage that would be connected to those terminal wires. That's going to be equal to the back EMF constant, KE, times the speed of the motor. And we have to just be careful with our units because our speed, we've been going in RPM. So we just want to be careful there. And then then you want to add in, so that's the back EMF part, and then you want to add in the voltage drop across the motor just because it has resistance. So that's plus I times R. You could substitute for the I. Sometimes you do this, and you end up with substituting torque divided by KT, so you end up with a relation that looks like this. And then you can say, well, if I held the voltage constant, and that would mean that you could plot speed versus torque, because KE and R and KT would be constant. A lot of times you see graphs like this where you have speed in RPM shown as a function of torque, and that actually would be of this line. This is for the 12-volt motor. I wanted to point that out. So, but we would have a similar thing at 6 volts for its motor, and this line would actually keep going until it hit the stall. For some reason, they like Micromo is showing that there's a little bit of a knee there, but that's not really the case with the equation. It's just a line that gives relates speed to torque for a particular voltage. So that's what that is talking about there. So what I did is I took the two scenarios. I took the current and said, okay, the two scenarios, one being loaded, two being unloaded. When there's a load, you want to take B57. That's going to be that torque needed at the motor shaft, the 5.14 millinewton meters, and you're going to take and divide by B63, so that's the torque constant. So there's my current that I needed at the motor right there. And of course, for the second scenario, when there's no torque, that means that there's no current. No torque, no current. So you have that. Going back and taking a peek at what the voltage of the motor might be for the loaded scenario, you're going to be implementing basically that equation. You're going to take B57, so that's this first part's actually going to be the torque. So you have B57 is the torque divided by the KT times D63 is going to be the resistance in ohms. So I've got these in my equations from Excel, kind of had them swapped, and then I'm adding in C57, so that's going to be the speed in RPMs. So to get into kilo RPMs, I divided by 1,000, and then I'm multiplying by C63. So that's going to be the back EMF constant. So that's how I got this. And it looks like 5.6 volts. So that it's a 6-volt motor, so that's fine. And it looks like for that particular scenario that going to the motor wires is simply the voltage at the motor times the current at the motor. So that 5 that we saw initially at the top of the page, that 5 watts is what's going to the motor, just as a point of reference. And then here I just repeated the same equation to show that unloaded voltage would be about 5 volts. You can get these voltages from a pulse width modulation of whatever your supply voltage is going to the motor. So that's how that would be accomplished. But I think that we have a chance here, with the exception of our planetary not quite having what we want. We've pretty much gone through and verified other aspects, so we're very close in our design of being able to, we're very close to proving that this device, this layout of the Micromo 1524 running at 6 volts with the planetary followed by a planetary feeding a worm stage with 4-inch arms would be able to deliver that 4-pound force, and also be able to close 4 inches in that 1.5 or 1.25 seconds. Here's another representation of the layout of the gripper. You have the motor on the input feeding the planetary gearhead, feeding the single start worm stage, feeding the fingers, the actual fingers, where the planetary has the 69-to-1, the worm has a 30-to-1, and the fingers have a 4-inch radius. In a loaded scenario, at the input you have little over 5 volts. You've got almost 1 amp, so it looks like about 4 watt, almost 5 watts on the input. That feeds out, and the motor load is a little over 5 millinewton meters. The motor spins at almost 2,000 RPM, and it's about a watt. That feeds the planetary gearhead, and the output of the planetary gearhead needs to be about 240 millinewton meters, about 29 RPM, so a little bit less power, 0.72. And then the output of the single start worm would be the 32 inch pounds. It's turning at about 1 RPM, and we're looking at about 0.4 watts. And then through the fingers, we actually consider it lossless there from the finger perspective. So this is a rotary to translational stage. In the output, we're looking at 4 pounds of force, and the two fingers are moving towards each other at 0.8 inches per second, so that the power is the same. And then looking at it from the perspective of a gear reduction, the input speed, actually we'd want to translate that into radians per second, the input speed divided by the output speed, in this case about 0.8 of an inch per second. When you divide the input speed in radians per second by the output speed in inches per second, you're going to get 1/8 inches. And that is really just 1/4, and then you divide again by 2 because there's 2 fingers. So that lays out the loaded scenario. And in the unloaded scenario, we really just have no loads that propagate through, so there's no current, there's no torque, no torque, no torque, and no force. And we're just looking at what will be the voltage on the input, almost 5 volts. We're looking at the motor spinning at 7,900 RPM. We're looking at the output of the planetary, or the worm, spinning at 114 RPM. Then we're looking at the worm gear and the finger rotation being about 4 RPM. And then the final fingertip velocity is about 3.2 inches per second. So that is another way to look at it. So in summary, we've shown you how to select an input motor based on the requirements of what the machine needs to deliver on the output. We sized the motor based on power at the output. We had to guess a little bit about what the system efficiency might be. Then we selected gear ratios. We used kinematics to match the unloaded speed of the motor to the unloaded speed of the output. Note, I wanted to emphasize, we could have used a different method there to select the kinematics. We could have looked at matching optimal power of the motor to what we have at the output, or the efficiency of the motor to what we have at the output, in order to select those gains. And then after we do the kinematics, then of course we can size everything based on the loads and the efficiencies. So anyway, that's one way of doing it. Hope you enjoyed it.